again, thanks IAS for inviting me, and to everybody online, apologies we didn't link it up maybe a bit better, but I'll make the PowerPoint available to anybody just to be able to download.
Online there.
Yeah, great. And as I said, hopefully we can maybe overdub this talk with the images. Now we've a lot of images to get through, so I'll do as best I can. This is just such a big subject. As Mick said, I did give a talk before on James Webb before it launched, and a bit of this talk is still that, but definitely then we got some results here. But I don't work for James Webb, so you always feel when you're going to talk about something you're not working in that you're a bit of a blow-in, trying to talk about something you're not working on. But that said, I think we've all had a deep connection and interest in the Hubble Space Telescope and what it has done, not just for astronomy, but to change our understanding and perspective of the universe, our perception of the universe in the last 20, 25 years. And James Webb is a natural follow-on from that. So I've had a very, very deep interest in that as being somebody who's interested in science outreach, science communication from the standpoint of, well, it's a really worthwhile human endeavor to do. So I'm following James Webb very closely, and hopefully can just share a few thoughts and a few insights about, what this telescope is about, what it's about to do, what it's about to unleash in the next couple of years, because it's barely gotten going. As stunning as the images we've seen, and we'll see them here, it is just beginning. If you may remember, Hubble took many years to get going before its most extraordinary results were achieved. So it's going to be the same for Webb. But to set some context, we're talking about Webb challenging the greatest questions in science to do with, I suppose, our place in the universe. So to set a little bit of context on that, we can take this from a number of perspectives. And I've many colleagues in professional astronomy who work with small telescopes, very often argue, why do we always start with the Hubble Space Telescope and start from there? So I'm just taking a particular thread or thought from before Webb to Webb, and that is what led to the Hubble Space Telescope? What discoveries did it make? And therefore, why did we start to ask, what's the next telescope to build, and how James Webb came about? So this is Edwin Hubble. He basically discovered that the universe is expanding, and therefore he inferred that the universe is expanding. Then maybe at one point in the past, it was smaller, and therefore, for the first time in human history, we really conjectured about the notion that there was a beginning to everything. And that wasn't just important from the perspective of the beginning of the universe, but therefore there was a beginning to Earth and a beginning to life. So the whole idea of this cosmic thread of time from some part in the time in the past to the present and into the future shaped modern cosmology. And not only did he actually discover the universe was expanding, but he discovered that the Milky Way wasn't the entire universe, but what were called island universes, which we thought were part of the Milky Way, were separate, distinct star systems of their own. And he even came up with a classification system for them. So basically he laid the foundation for modern observational cosmology, and along with Einstein, theoretically laid the foundation for, one of the two great pillars of our modern understanding of the universe, the other being quantum theory, but general relativity and cosmology. And we're still entangled in that. Most of the big questions are not answered, but we've learned a huge amount along the way. Now, before we get to then naming Hubble in his honor, it's worth remembering that there's an entire armada of space probes in space telescopes and on the ground. So again, the point is that we haven't got to Webb just from Hubble. So so this is the European Southern Observatory, of which Ireland is now a member. So young researchers here can now go and actually pitch for time on this. We pay several million euro a year into it. There's Europe's great Gaia, currently tracking 1.6 billion stars in the Milky Way at incredible precision astrometrically, spectroscopically, and photometrically. So giving us brand new insights into the universe, into the Milky Way. Spitzer, the infrared space telescope that came before Webb. This is WISE, another infrared space telescope. Herschel, or is that Herschel and WISE? And then Kepler, which discovered so many exoplanets. Most of these aren't working now, but they were working over the last 20 years, along with, of course, the great Hubble Space Telescope. Now, we've all seen the iconic images of Hubble, but more, I suppose, important is the discoveries it's made. And, as important, because I suppose the visual perception of the universe is really important to all of us that know where we live. But Hubble really did define, a number of big questions to ask, has set up a set of new questions, and actually answered some old ones. We didn't know how old the universe was until Hubble was launched into space. this expansion rate called the Hubble constant, we didn't know, was varying wildly, and Hubble pinned it down and therefore discovered that the universe, as far as we know what the universe is, very confusing that these days, but at least the Big Bang happened 13.8 billion years ago. That's the origin of a meaningful universe. It revealed galaxies in unprecedented detail. It discovered that these type 1 supernovae, which are kind of like a celestial candlestick, so things get dimmer by an inverse square law, the further the dimmer. So if we see these close by and know how bright they are, and therefore how far they are away, then we see them on the far end of the universe, we can actually work out distances to the far end of the universe. And what Hubble discovered was that the universe at the far end is expanding faster than it should be. And therefore, that there's this kind of dark energy pushing the universe out. So it gave one some of the strongest evidence for that. Again, we'll see some of these deep field images where they kept the telescope pointing in one direction for up to 2 weeks and revealed galaxies where we thought was simply blackness, nothing. And how close to home has looked at nebulae in unprecedented detail, protoplanetary disks around newly formed solar systems, and even imaged some exoplanets as well. Let's take a look at some of that. This is the Great Deep Field, January the 15th, 1996. I remember I started a new job, Sun Microsystems, and they had nothing to do. And they sat me in front of a computer, and I just Googled, 96. The web only came around 92, so the web was early. And I was 33, 57 now, so I was 33 then. And I remember looking at this image, and I was interested in astronomy since I was 7, and thinking, I don't recognize this. And after 15 minutes, the hairs started to stand on my neck. I suddenly realized, oh my God, something fundamentally new has happened here. Hubble has imaged galaxies that we couldn't see from the ground. And this movie will demonstrate what we're going to say. So here's an image you might see through really great binoculars in the southern hemisphere, or southern part of the northern hemisphere. But I'm going to let it run and then pause just there. Can you see other stars now behind these ones? So let's think of this as best an amateur can do. Now we're into the realm of stars that a professional telescope on the ground, pre-image stacking, could see. Just stars, professional telescopes on the ground could see that amateurs can't. And then Hubble went and did it all over again. This is what the best telescopes on the ground could see. This is the deep field. You can see the layers of perception that Hubble brought to us. And by the way, James Webb has gone behind that again. So this is what we mean by kind of a paradigm shift, that Hubble really changed the way we view the universe. We could see almost nothing, and then it revealed, of course, then these galaxies in their billion, in the far end of the universe. We're talking about 10 to 12 to 13 billion light years away, or 13 billion years ago. Just to put this in perspective, that's about an area about the size of a grain of sand held at arm's length in the sky. And if Hubble were to image the whole sky at that resolution, it would take it 900,000 years to do it. It also discovered massive galaxy clusters. This is not gas, this is trillions of stars that are bending space and time. And indeed, as massive as all the stars in that image are, they're not enough to bend space and time. So these images, the fact that we're actually seeing here gravitational lens, these are all images of the same galaxy behind this cluster. And it's like you're acting like a lens, and in our line of sight, we're seeing the same galaxy multiple times. They've estimated up to decades in distance. If we could actually build a telescope big enough, we might see some alien civilization there, and then 20 years later there, same planet at different time. But actually, because there isn't enough mass, stars-wise, it's also evidence of what we call dark matter. So we can measure the amount of dark matter in that cluster using Hubble. Now, closer to home, of course, to give these magnificent images of galaxies colliding, and of course, nebulae within our galaxy. And this is the beautiful Eagle Nebula. Most of you have been at talks about me before. I know where I'm going with this because I'm almost obsessed by the pillars of creation. Here was Hubble's beautiful. Actually, this is the 25th anniversary image of the pillars of creation by Hubble. This is the original one 25 years earlier, at the very tip of it. And I spent about, I spent 20 hours doing this. Take a look at that. There's a paper written on this, but they didn't align it. Can you see the movement? Take a look at here, 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 and here. These are two images of the pillars of creation, 25 years apart. Can you see the movement? There are solar systems forming. You're seeing this for the first time, well, second or third time. Nobody published this. You're seeing. So basically, there's stars being born there. And what happens is, well, we don't know the full mechanism, but basically the stars are spinning in this direction. And what's ejected from their poles, we think through magnetic phenomena, they eject hydrogen gas and dust. Hydrogen atoms, molecules, molecular and atomic gas, and dust. What I find amazing about this, there is a paper written on this, is that, by the way, the movement there on all fronts is about 60 billion kilometers, right? So from here to where it moves to is 60 billion kilometers, about 10 times the width of the solar system. Look, there's a geometry to this. They're all moving in the same direction. What's going on? There's something in that nebula that actually kicked off the motion. It's connected like clouds on the Earth. They're all moving in the same direction. This is a system. And that's what we try and understand. This is what the likes of Hubble gives us. You just can't do from Earth. Images over time. I just thought I'd put in on the tiny little pillar, that's about the size of the area that, well, it's bigger than how far Voyager has traveled from Earth. And then I just thought, Carl Sagan, pale blue dot. If you divide, I worked out, you'd have to divide that square up maybe around 10,000 times to see Earth as that. We've a lot to get on with it. I won't read the quote by Carl Sagan. We'll get back to it. But to finish this kind of whistle-stop tour of Hubble, I just thought I'd show one other image called the gigapixel image of the Andromeda. So when we look at Andromeda, it's a beautiful galaxy. Again, it always blows my mind. I only learned this in the last few years, that actually in the sky, if it was bright enough, it would be 8 times the length of the moon. It's not small. It's huge in the sky, just very dim. But the smallest thing we can see on this, although we accept this as a galaxy, the smallest thing we can see on this is about 100 light years long. Nothing smaller than that is resolvable in this image, and that might be even generous. And the reason why I show this image is that's what happens around one star. That's our own solar system. So what's going on in there? And this is where I jump out of my PowerPoint and bring up the Hubble billion pixel image of Andromeda. It's zoomed in on part of Andromeda galaxy, but of course, when you zoom in on this, hope I can, you start to see the individual stars. Every star in that, every speck is a star, like our sun. And every one of them is separated from every other star by the distance of the stars in our sky, by the way. They're not right next to each other, So this is what Hubble gives us, a different perspective beyond ground-based telescopes. But also this image I used to show kind of the transition, the limit. Because if you keep zooming in, you realize you're actually not looking at stars. You're looking at pixels on an image. They represent stars, and I've worked it out. Each pixel is 2.9 light years. That's what Hubble can see in Andromeda. Nothing inside 2.9 light years. So there's, as amazing as Hubble is, there are limits. So it gives us a new shift, new understanding of the universe, but it doesn't do everything. So then to go back to the PowerPoint, I can find it. No. That's why, as great as Hubble being, and actually, by the way, I'll skip this. I wanted to, let's very quickly mention that, of course, exoplanets are a big question today, and not just from Hubble, but from Kepler as well. And indeed, actually, a beautiful project called Pale Red Dot on the European Southern Observatory is to try and find planets around nearby red dwarf stars. And we have found, of course, that our nearest neighbor, Proxima Centauri, has an Earth-sized planet orbiting it called Proxima b. And we can't study them in detail. We don't have the resolution or sensitivity that we might think it might look like on the surface of it. So this is, I suppose, where Hubble stepped into asking new questions. When did the first stars in the universe come around? How did the first galaxies form? How do galaxies evolve over time? How do stars and planets actually form? I mean, very often you ask people, how does life form on Earth? They say, a soup gives us a bacteria or a microbe. But that you're talking about the inanimate world giving us something with 200 trillion atoms that can self-replicate. That's the amazing bit, and we know nothing about it. Likewise, we tend to say, oh yeah, stars and planets come from nebulae, but how? We don't have those answers. And that's the next step for the next generation of astronomers. And then how many exoplanets are there in the Milky Way? We're estimating, what's it, 2 trillion planets? So you hear some people say 40 billion Earth-like planets, all this sort of stuff. Well, we don't know. You know, this is the thing. And these questions, I need to get onto the Webb images because they are already delivering extraordinary results. So Webb will ask questions about what is the mineralogy on the surface of exoplanets? Do they have oceans? What are their atmospheres like? Even what's their climate like? It's answering that question for some exoplanets right now. And can we detect biomarkers? This question, I think, is actually becoming a little bit naive. Are there Earth-like planets? You read elsewhere that habitability might be a much broader thing than just Earth-like. So we then have reason to go beyond Hubble. But the thing is this, and I'm going to go through the next few slides. I have a lot of writing slides here, but I'll say them, otherwise we'll be here all night. The thing is, the objective is not just to build a bigger optical telescope. And here's the reason why. If you go back even to the pillars of creation, we can't see inside this gas and dust. It's very dense and thick. What we're seeing mostly here is a reflection of light off nearby stars, off the clouds of gas and dust in this nebula. Now, it turns out that if we build a telescope that can see infrared, we can see through the dust. It's not really we can see through the dust. It's that whatever's emitting infrared in there can pass through the dust unimpeded, right? The same way as if there's a hot spot, you know, and you put a cover on it, you'll still feel the heat through the cover. Heat gets through things. So the thing is that we realize that if we want to see things being made, if we want to see dynamism, if we want to see, you know, the actual dynamics of the universe, the moving universe, the universe making things, creating things, then we need to move out of the optical and look at the emissions of infrared or heat that they're producing as they do things. And the thing about it is this, is that, in kind of explaining this to non-science, that infrared and light are almost identical. They're, like, infrared is just longer rays of light. We think of it as very different because we sense it with our skin. We don't see it with our eyes. But well, we all see the Gardaí helicopter cameras at night that pick up, you know, the criminal on the run, hiding under the bush, and they can't because their heat is being emitted off. And you get to see them very easily because they're emitting infrared. Also, you might notice that those cameras are always quite blurred, and that's because infrared waves are very long. So it takes very big lenses or mirrors to capture them to give you a sharp image. If you use smaller cameras, then you get blurred because the waves of infrared light are longer, and we'll come back to that in a minute. So the thing is that we said to ourselves, we're going to build a new telescope. Let's not just build a bigger Hubble. That might happen in the future. There's a reason for that. Optical's good. But nevertheless, if we want to see inside nebulae and see stars and planets being born, we want to see anything moving, just rub your hands together, you generate heat. Anything that changes generates heat. If you want to observe change and dynamism in the universe, build an infrared telescope. But there's a second reason to build an infrared telescope, which is because the universe is expanding through what's called a Doppler shift or Doppler effect. Things that are moving away from you stretch the waves they send towards you. So if you've got a normal yellow star right next to you, it'll appear yellow. But if it's moving very fast away at the far end of the universe, it stretches its yellow waves out and they become red. So you see things red shifted. And indeed, most of the optical objects like galaxies that we would see with our eyes nearby are actually gone beyond the red into the infrared at the very far distance of the universe. And the very far distance of the edge of the universe corresponds back to the beginning of time because we're looking back in time. The further out we view, that's another talk. All about that, that's a brain twister. So we want to build an infrared telescope to see early in time, far out in the universe, because objects are moving very fast away from us. They're red shifted. So this is just a demonstration to show that here's a person and you're seeing, the optical reflections of whatever light's in the room on them. Here's an infrared image. And first of all, the heat passes through the bag. And then, there's lots of blood activity in the brain. So we see the activity through the heat map. It's a broad demonstration as to how infrared gives us a different perspective on the same thing. Both are valuable. We're not rubbishing Hubble here. We're just saying that infrared gives us a new perspective. And again, that's just a diagram showing that we get this red stretching as we go to the edge of the universe. Now, we've had, as I said, infrared telescopes in space. Spitzer is a beautiful telescope, 0.85 meters. Webb is 6.5 meters. And it did remarkable work through the noughties. So there's the Sombrero Hat Galaxy. There it is in infrared. It just gives a different perspective on it. This is an amazing image. This is one of 16 images of the Milky Way galaxy. Well, when I say this is 50,000 infrared images of the Milky Way galaxy. The entire Milky Way, it's 800,000 images. And all the green in that is organic carbon as organic molecules. We now know from Switzer that over 90% of the interstellar carbon in the Milky Way is bound up in organic molecules. In fact, the Eagle Nebula is over here. Actually, I think I might have it on the next slide. I do. So there it's seen Eagle Nebula, and you can see Switzer could see Eagle, but with about the same resolution as a really good ground-based telescope. But look at Webb, or the Pillars of Creation, we didn't see all those blue stars. Sure, we didn't from Hubble. It's seen through the actual dust. And actually, most people don't realize Hubble has a near-infrared camera. So there's the Pillars of Creation in optical. There's the Pillars of Creation in near-infrared. There's the stars in the nebula. You can't see with optical. This drives the point. See, they're really there driving the dynamism in this nebula, and their Hubble's near-infrared camera picks them up. But Webb will just do better. So there's James Webb, beautiful telescope. So it's 6.5 meters. It's painted gold because gold reflects red well. Why it's gold in color. We heard of this tennis court sized heat shields. We'll get back to some of the characters a bit later. There's 5 of them, and each one is only 1/20 of a millimeter thick. About the size of a tennis court, and they have to roll them out. There's 151 or something motors on this. The possibility of failure was just enormous. And we'll talk a bit more about characters in a few minutes. This is James Webb. He was the second administrator for NASA, and he basically managed the Apollo program. But he retired in 1968 before the first person landed on the moon. But I knew of him before he was going to be linked with James Webb, because in writing my book about Mars around 2003, 2005, the editors, I pitched, I'll tell you a very quick anecdote. I gave a talk about Mars down in Cork on 2003. Remember, Mars was closer than 54,000 years. And then I met a friend from college next night. We're just out for a bunch of us for a meal, and my friend Nora Hart, he said, "Oh, you should have written a book about Mars." Oh, well, it's too late now. So I went back home and thought, God, she's right. Went on to Springer, wrote a pitch, and at 10 o'clock the following morning, I went on Amazon and noticed there was no books written on Mars in 8 years. That was the clincher. I'm an unknown author. And they got back to me at 10 the following morning and said, "You're right. There's a hole in the market. Here's the contract. How long do you think it'll take you to write?" And I've written a few articles for astronomy magazines, and I multiplied it up and thought, about 15 months. 7 years later, still doing it. I realized I couldn't write. And then they applied 5 astrophysicists, including 3 Mars scientists, to referee the book. So it was a real learning curve. But I learned something about this guy. Basically, when Carl Sagan and co. told NASA to go to Mars in 1965 and they discovered craters, they realized Mars was dead. NASA recoiled and thought, we're going to cancel our space science program. Lyndon B. Johnson, got the Werby Jerbies about it. James Webb basically had one meeting with Lyndon B. Johnson and saved civilian space science. Not only did he leave the meeting with the Mars program surviving, but he got the money for the Voyager program as well. And then shortly after, Hubble started to be developed. So that's, even though he's an administrator, he really did single-handedly save space. He wasn't even like, this idealist. You know what he actually said to Lyndon B. Johnson? The minutes of the meeting are online. I read them. Basically, he convinced Lyndon B. Johnson that if you shut down the Jet Propulsion Laboratory, you're going to lose 30,000 human years of space science experience in a Cold War. So James Webb, or Lyndon B. Johnson, realized, keep it going. That was the pure politics, but he knew what to do. Anyway, the thing is that, what I will say is that James Webb, it's the first telescope built to look back to a particular period of time, the beginning of time, at least practical time, the first stars. A huge objective for it is to identify the first stars in the universe. Now, that will be a big Nobel Prize winning project if they achieve that. That's like the Higgs boson for CERN. It's also got to try and identify, how do galaxies form? Is it black holes, then the galaxy, or is it galaxies, then the black holes? It's to observe planet and star formation from the very beginning, from the coldest nebulae. And it's actually, I'll show you some results. It's starting to work on that right now. It's going to try and actually analyze the composition, the surface, whether there's oceans, atmosphere, and climate of thousands of exoplanets. It's going to, if there are biomarkers on exoplanets, it will find them. It's that good. And it's, people don't realize this, it's going to revolutionize solar system science. It's going to spend 7% of its time monitoring trace gases on Mars, the climate of the gas giants, all of the icy moons, Pluto. It's going to map the mineralogical context of all of the asteroids, the Kuiper Belt objects beyond Neptune, and give us our first census of the material makeup of the solar system, which we don't really have. So it's going to be, as I say, looking very close to home as well. And I just go through that in a bit more detail there, and I'll skip that. Actually, this really impressed me when I saw this graphic like this. There's Hubble's mirror, 2.2 meters, isn't it? 2.5 meter, 2.5 meter. 2.4, yeah. And there's a person, and then Webb's a 6.5 meter, huge device. So just the broad points to it, it's primary mirror 6.5 meters, focal length of 130 meters, huge focal length. It's pointing away from the Earth the whole time, and built behind it then are its instruments. And this set of 4 instruments are a pinnacle of human engineering. You do not get better. I'll just quickly say what they are. NIRCam is the star of the show. NIRCam is its imager in infrared. So it's like the camera that will give us the visual images, but in near infrared. It's a sister camera on Hubble is the wide field planetary camera, the one that gives all the amazing images. So if you're looking for images, it's always NIRCam. Now, it's not the only one, but it's an extraordinary instrument that will give in infrared, where the waves can be up to 10 or 100 times longer than in visible light, Hubble resolution. And indeed, in some circumstances, better than Hubble resolution. You see, another instrument can get 10 times better than Hubble that way. Then working very closely with it is NIRSpec. This is the spectrometer. Now, let me just very briefly try and give you, a crash course in spectrometry. So, the old sodium lamps in our streets are orange, aren't they? They're orange because they're sodium. Every element in the periodic table glows a different color if you illuminate it. So we can infer the material makeup of something from the color it glows. Now, there are millions of shades. So when we look at an object that glows, that emits its own light, and we analyze its color, we can tell what it's made up of. That's what remote sensing on the Earth does as well. Thermal cameras looking down, and if we know the color that potato blight has, we'll see it on the landscape. We'll say there's potato blight there. Well, this NIRSpec is doing the same thing. It's just looking at exoplanets, and from the colors that it's emitting, that each exoplanet's emitting, it can infer what are the materials that make up that object. Now, this to put this in context, if you think of, say, what 3 filters do for us to give us colored images in normal light, this spectrometer has 29 filters. So it's got this amazing, what we call spectral resolution. It can really fine-tune its viewing to any number of material setups, from looking at trace elements in the atmosphere of Mars to understanding what molecules are being manufactured in the first stars in the universe, the far end of the universe. Extraordinary workhorse with NIRCam. Then MIRI is the one Ireland's involved with through Professor Tom Ray and Dr. Patrick Kavanagh. And this is, they're all stars of the show for different reasons. Webb is cooled down passively to minus 50 Kelvin, minus 260 or thereabouts centigrade. But this is actively cooled down to 7 Kelvin. So it's unbelievably cold, minus 266 centigrade. And as a result of that, think of it this way: if it's at 7 Kelvin, it can see anything that's hotter than that. It'll glow infrared. And this is going to be the clincher to see the first stars in the universe. And there's a special technique it's got called Lyman dropout. So basically, we know exactly how we're going to find the first stars in the galaxy, in the universe. So when stars are born, they're surrounded by hydrogen, right? And that hydrogen absorbs the light and you can't see it. Now, if we're nearby, that's actually in the ultraviolet. But because the first stars will be red shifted, actually, we see the cloud around them cut off their infrared because it's stretched from blue to red. And we know what wavelength in the infrared it should be. So in other words, when we go look at stars that are at a very high acceleration from us, that tells us they're very early, and we see stars that are emitting their light, but it cuts off at a very specific wavelength of infrared light, we'll be able to say new stars at the beginning of the universe. There's 2 fingerprints, and Miri will clench it. So Ireland built the filters for this, and as you've probably heard, there's a bit of an issue with these. There's friction, they're rubbing at the moment, so they're having to devise a new observing regime for that. I don't think that's Ireland's fault, by the way. We made the filters, we didn't make the mechanism that actually put them in. And in fact, Webb was 10 billion over budget and 10 years late. It was supposed to be 500 million, cost 10 billion, 500 million. And it was supposed to be launched in 2012, it launched in 2022. So, but Ireland delivered their filters under budget and on time. Okay. And then, as I say, Professor Patrick Kavanagh is involved deeply with it right now, commissioning the instrument. They wrote the software to analyze the data on it and so forth. We move on very quickly then. The final instrument is called NIRIS, and it can actually basically do a thing called, aperture masking interferometry. So it can basically make the James Webb Space Telescope act like it's an infrared camera 15 meters wide, not 6.5. It improves on the optical capabilities of the device. So this is what we use for very, very sharp imaging. They reckon it could see individual volcanoes on Io. That was a little simulation. This graphic just shows that looking back in time, Hubble could see galaxies around 10, 12 billion light years at a stretch, 13 billion. Webb, we're hoping we'll be able to see to 13.6 billion years ago. The thing is that last couple of 100 million years gets ever and ever harder to see. It's like you're looking into ever more dense fog because the galaxies are moving ever faster away from you and stretching their light ever further into the infrared. So to get this last bit of observations to the first stars, we need Webb. I'll just skip 1 or 2 more images here. Again, I don't want to labor too much, but basically these few slides shows how we'll do this. In fact, when a planet moves in front of a star, if it's got an atmosphere, we'll actually notice that the light won't cut off immediately. It'll fade. And in that moment of fade, we'll be able to observe the star's light passing through the atmosphere, and we'll analyze what was removed by the atmosphere. What's called absorption spectroscopy. And that's how we'll actually tell what's in the atmospheres of far-off planets. And these are slides I had in the talk I gave before, and I purposely left them in because it's done what these were proposing to do. It says, James Webb Space Telescope will analyze infrared light from stars dimmed by planets passing in front of them. So remember that. James Webb Space Telescope will see the unique fingerprint of each chemical element present in the exoplanet's atmosphere. Remember that. And James Webb Space Telescope will tell us about the atmospheres of extrasolar planets. Okay, and there's one more I want to just say is James Webb Space Telescope will observe rings and small moons in our solar system. We've seen the images of Uranus, something with its rings, and I'm going to show you that. Studying structure. And so therefore, all they were the kind of proposals as to what it will do. And let's go hopefully take a look at some of those. But before we look at the results, just let's take a look at some of the images of putting it up and launching it. So there it is in all its glory. Magnificent, isn't it? That was never going to cost 500 million, Sean. And there's the shields rolled out. They had to put it in an anechoic chamber, or not an anechoic chamber, it's kind of a thermal chamber, and bring it down to 50 Kelvin and leave it there for weeks on end. But the thing is that it's there at 50 Kelvin forevermore. That kind of extraordinary testing that costs a fortune can only test the mechanical electronic capability of this device so far. So the thing is to remember with these instruments is that there's about 6 glitches with it already, and there will continue to be. My PhD is I wrote software for a 5 centimeter camera on ESA Integral, actually by Professor Lorraine Allen here in UCD, 5 centimeter, and the number of problems we've had with it over time you wouldn't believe. 5 centimeter, and this is 6.5 meter. So there's the instrumentation pack. It's already been winning awards. This is one, as it's difficult to explain when you just look at something like that, what it involves. It's the greatest of human ingenuity, engineering-wise. They had to roll it down all up and put it in an Ariane rocket and send it out to a place called L2, 1.5 million kilometers from the Earth, in a stable location where the sun's and the Earth's gravity broadly cancel. And so it'll broadly stay there, but it needs thruster fuel to correct its orbit every so often. And ESA did such an amazing job at launching it that they saved on that thruster fuel in getting it there. And they basically announced recently they reckon they can get 20 years out of James Webb. They forecast maybe between 5 and 10, but they reckon they have enough thrust of fuel to make it last 20 years, which is extraordinary. Again, some images of it leaving Goddard Space Center through the Panama Canal down to French Guiana. And then this is an animation which you can see online, and it's worth watching. Just go, Hubble or Webb launch animation. I mean, within a few minutes, it was exposed to the outside. There was no protection of it, and it was unfolding within just minutes. And then they called it, was it 29 days of terror, because it had to unfold. You see there, 5 days, 14 days, and by 15 days it was fully open, and then arrived 1.5 million kilometers beyond the Earth. Now, this graphic shows the orbit, and actually, this isn't me cutting it. I went and looked at the original graphic, but it looks like it's cut on the base of the orbit, but it'll all become a bit clear a bit later on. So it's not my PowerPoint cutting it, just the way the graphic is. So you can see Webb here orbiting this L2 point. So it does orbit this point, and this is better shows it. So it's pointing away from the Earth and the Sun, can never steer towards them, and then it orbits this point. That's the Earth, that's the Sun, and it's so it's the Webb telescope is on this side, the heat shield, and the little radio antenna transmit back on the far side. If it ever turned around towards the Sun, all its instruments will be destroyed basically instantaneously. They just heat up too much, so it can never look towards the Earth and the Sun. And here are some of the results. So, of course, we saw these images in July, was it the 12th, I think, last? So, to put this in context, this is an ultra-deep field. The galaxies in this image are around 13 billion years away, are old, so 13 billion light years away. Now, to put this in context, this is 12 hours observation time. For Hubble's deep field, it took 2 weeks. Now, not 2 continuous weeks, but hundreds of hours. So Webb was seeing deeper, and in fact, Hubble was seeing about 3 billion light years closer to home than this. It was taking months to build images like this of Hubble, done basically in a day. And then we're able to actually determine the distance of the different galaxies by through what we call it, here's the red shifting. So they're able to see spectral lines for oxygen and hydrogen, and then notice that those two lines are shifted towards the red the further away the galaxy is. We're seeing those spectral lines being pushed further away. Not only that, but to get spectra of galaxies at that distance is unprecedented. So we're already measuring, for example, the amount of oxygen being manufactured in the first galaxies in the universe. In fact, they just only last week detected the most rarefied object in the universe with only 2% oxygen. We've never measured less than that. And there's an example of what it can do to look at these pieces of light from the light and all the filters it has, infer what elements are in those galaxies. Now, we've never seen this before. These galaxies are only a few 100 million years after the birth of the universe, and we already know it was synthesizing heavy elements beyond hydrogen, helium. These were being manufactured within stars. Very big stars that were exploding. They were fusing, causing through nuclear fusion, making these elements and then emitting them into the interstellar regime, and then we're detecting them 13 billion years later. That's my alarm to tell me I'm 45 minutes to go, or 45 minutes, and so let me keep going. Here's how it observes an exoplanet. Remember, it said it will observe. So there's an actual observation of a planet moving from the star. Now, it was an already known exoplanet, but just proving the point. But what Webb went and did was, and this took about an hour's observation, measured what's in its atmosphere. We know that this is a carbon dioxide-rich atmosphere, and that exoplanet. Same release, this planet, WASP-96b, it's a very hot planet, so it's a bit like maybe Venus in terms of its atmosphere, but water in the atmosphere, clouds in the atmosphere. That planet's 1,000 light years away, and in an hour's observations, it basically analysed what's in its atmosphere spectroscopically. Then it said we'll observe rings and moons. So here's Uranus. I mean, two things about this image. One, all telescopes have their resolution limit. Not the crispest image in the world, but nevertheless, it's seeing the illumination. This is not reflected sunlight. This is what's going on at Uranus that's hotter than 7 Kelvin, or well, maybe 50 Kelvin. And we can now monitor the moons, measure their material makeup, and even the rings, which it took Voyager a lot of effort to see those rings even close up. And Jupiter as well. And extraordinary image here. This here is the moon Io is being turned inside out by Jupiter, and there's a torus of sodium, silicon, is it? Sodium torus and it carries 1 trillion watts of power that bombards the poles of Jupiter. And there we are actually seeing it in infrared. So Jupiter's poles being bombarded by Io's, a conducting loop between the poles of Io and the poles of Jupiter. And then we've got the pillars of creation, of course, seen by Webb. And what I want to do is jump out here and just, so, it looks gorgeous as well, like with Webb or like with Hubble. But when we just step into, we'll find it here, the highest resolution image, and you can download all these, again, we can zoom in, look at the number of stars and the resolution of the stars. They're the new stars born in that nebula, right? We can now go start analyzing the motion of these. Remember I showed you movement. In fact, one of the things I should point out in the image was, if you had seen the background stars in the two images I showed moving, you saw proper motion of the stars in the field. We'll be able to monitor, so you can just keep zooming in. The detail is just spectacular. There was that little finger of dust I had in the Hubble one. So you get a sense of the improvement of resolution here. I'm actually behind time and it gets better, so let me move on very quickly. So there's, I just put the three of them together. I'm noticing when I align Webb and Hubble images, there's a slight geometry twist. I thought there's something going on. MIRI, the camera that detects very cold, that's its image of it. So it's filtered out all the hot stuff and it's showing the coldest dust. And these are the regions we'll be looking at for the birth of new solar systems, the coldest regions of space. To move to this is called the Carina Nebula. It's 200 light years across. It's in the Carina Sagittarius arm of the Milky Way galaxy. And I want to focus in on this little section over here because what we're going to actually arrive at later on, I can't really see it in this image. Oh, no, that's not, I beg your pardon, sorry. This is the actual Tarantula Nebula in the Large Magellanic Cloud. So I'll just, now this is the best you can do from the Earth before image stacking. So ground-based telescope can do better than this now. There's Hubble, there's Webb. So Hubble and Webb, they're not better, it's different. There is a bit more resolution there. And then what we can do, however, with Webb is infer the different materials from the different filters. Let me move over to Carina Nebula. So actually, I want to just show you. So we're here, Eagle Nebula is around here, and I'm looking over to Carina Nebula just over here, about 8,000 light years away. You can see why I got confused now, can't you? They're very similar. So I want to concentrate. This is an amazing area of the Milky Way. It's the most active star-forming region in our Milky Way galaxy. It's one of the most studied regions of the Milky Way galaxy, and it's about 200 light years across. And I'm going to concentrate on this little central region here. So what I've done is, again, rotated it down. So there's that square angular part here. And there is the best we could do before image stacking from the ground. There's Hubble. Let me just go back again. It takes a long time to align these. Now let me step out of my PowerPoint and into this, because this is a 29,000 pixel image. It's absolutely incredible. I did. So I'm going to sit down for this. You could spend a lifetime on this image. You know parts of it. You've seen them on posters and calendars. There's Mystic Mountain. Let's zoom in on it. Recognize it? There's new solar systems being formed. Webb is going to analyze all of this, but there's thousands of stars in there. Hubble can't see that Webb will see. Zoom back out again. Eta Carina, one of the brightest stars in the entire, it's two stars, each massive. So you've seen this more, so it's two stars orbiting each other, flared up in 1837, and they're 5 million times the luminosity of the sun. Now, the thing is, I'll just highlight here one of these. So, for example, if you take, for example, down here, the base of where my arrow is, you can see kind of a cliff edge there of dust. And we're now realizing we're getting these kind of edges where hot stars in this nebula are basically vaporizing. They're actually ionizing the gas, and then therefore the nebula boils off and away. Now, let me just, you can work through that image. It's all free, available online, so you can download all of these and study them for yourself. Let me just step back into the PowerPoint. So the thing I'll go back is, we've all become aware of probably one of the best images of Hubble Webb is the what's called the I actually have a little laser pointer here. I don't know where it is, but anyway, actually I'm sure I can use my pointer here. We heard what's called the cosmic cliffs are up there. So Hubble has images, but I couldn't find that image online. But I want you to keep a note here. There's a tiny little star somewhere around here and a little glitch. So this is where we're going to move into. This is where Webb concentrated on. There's Mystic Mountain. Yeah, so I've got it there. So this is kind of where, brilliant, thank you so much. So the famous Webb cosmic cliffs we're going to look at as really the last section of this talk, so we're getting there, is this little region here, that star and that little piece jutting out there. So here's Hubble's image of it. There's that star I pointed, and there's that little piece of cloud, and that's a pretty impressive image compared to that. Here's Webb. So Webb basically steps into this and again can see through the dust and reveals the stars that are actually in the image. And these are brand new stars. These stars are only 50,000 years old. 50,000 years old. They're brand new. And I'll just step out of it and for the last time and go through an image, go through that one in high detail. Because it doesn't stop there. You can zoom in on this and you just start to see the techno. Remember the movement I showed you in the pillars of creation? So like we're down at the 10 billion kilometer level here. We will see movement in this over the 20 years of Webb. They'll return to this and observe movement. If I pull out, actually, one thing we're realizing now is we're now understanding is you can see actually the vapor world, the ionization, the gas coming off. In fact, only last week, no, not just before Christmas it was, it produced, so that's NIRCam, the star show. That's through 8 filters, infrared filters. Here's the same image through 3 filters. And it reveals even more detail because now you can absolutely see the ionization. These stars are basically burning off the edge of the nebula. And as they do, they cause dynamism and new solar systems to form. So we can actually see here in this image, these little red areas are actually, in fact, they're coming from this star on both sides. I'll go back into the PowerPoint and show you. But we can get and zoom in on this. You see how far we're going, can go beyond Webb. In fact, you're seeing the diffraction pattern of the James Webb Space Telescope optical limits here. You know, we're pushing the instrument to its limit. But, you know, you can just see the resolution and quality of these images. They're just mind-blowing and how they go beyond Hubble. So Hubble was showing us beautiful, the Carina Nebula, but we were seeing, kind of brightness there and a bit more darkness there. This just reveals the detail in extraordinary detail. And as I say, this is only since July, It took Hubble about 4 years to give us the pillars of creation. What was it, 95? It was fixed in 92, 3 years. So, this is barely scratching the surface. We're only getting going here. So let me just, we're nearly there, guys. So I've just kind of got a sequence of images to show how they're already analyzing this image. So that's the original from ground image revealed the best I could. And there's Webb through NIRCam. And here it is through MIRI, the one Ireland's involved. And it's different again. And what's different here is it's different infrared and different filters. So we're actually seeing even more to this. It's hard to see in this image here. Any star that's red, there's lots of them here, and on the one you see in your computer screen, you see lots of red, are new solar systems forming. And they're literally inside the dust that even NIRCam can't see. So Webb is improving on itself with combining MIRI and NIRCam. And as I say, these are, by the way, this is called the early science program, just to figure out what can Webb do. There's 13 science programs going on right now. And they'll continue for the next couple of months. And then after that, then they'll sit back and say, right, now let's get started. And it's already doing this, quite extraordinary. They're just kind of superimposed 8 filters, 3 filters. And with 3 filters, you're just seeing the light or the infrared. And again, this is a combination of infrared reflections from other stars, but also a huge amount. So there you can see red. That's hydrogen being blasted off a new star there. In fact, actually, I think I might have actually given it here. So yeah, here they've zoomed in And then they've removed the stars to see, there's the new star, and there's the clouds of dust being blown off it. And they've detected about 12 of them just at the upper edges of this. And in fact, even there you can see actually the ionization on the edge of the nebula occurring really clearly as well. They had hypothesized this with the Orion Nebula, and we're actually now seeing this ionization. In other words, we didn't know whether these nebulae were kind of basically shrinking from the inside or from the outside. Now we know these stars are burning it off, and they're triggering solar system formation. And these are just the last few images. So this is taken. This is of a piece of a nebula called it's called Chameleon 1. But this is one of the coldest images ever seen. It's only, again, about 50, 60 Kelvin. And it's a nebula where we're now seeing, and we never knew this until this result was only released this week, freezing ices of ammonia, methanol, methane, water. So, we've known that we've had molecules in nebulae. Now we see ices. And what this is called the Ice Age Project, they're going to call it, for James Webb. And what they're going to try and do is find nebulae all over that will allow us to monitor the formation from ices that are of all of the volatile materials that are important to life and planets like rocky planets. And then can they see that evolution through into the formation of the first comets and maybe planetesimals, and lead us to understand how solar systems form. Again, this is just an animation showing that this is the ultra deep field they released in January 12. They've looked at 3 galaxies in it that are at 13.1 billion light years. They're just 600 million years after the age of the solar system, and they've compared them. This is a beautiful merger of James Webb and citizen science. So citizen science is where people get involved, and one of the great pieces of citizen science was Galaxy Zoo. Chris Lintott, who does the Sky Night, had a great hand in this, and he might have even formed it, whereby through big surveys, there's a big survey called the Sloan Digital Sky Survey, they ask people to spend a bit of time going through them to classify different galaxies. And these nearby strange galaxies were found through Galaxy Zoo, called Peapods, and they're like little proto-galaxies where there's an extraordinary amount of star burst happening there. It's blurred because it's not a great image, but extraordinary amount of star formation. And the Webb guys only the last few weeks decided they thought saw 3. Now there's a Peapod at the edge of the universe. It's reddened. If that was close to us, it would be that color. And they actually mapped up their spectra, and they found they're identical. I mean, a galaxy forming at the beginning of time has an identical spectrum to one that this is 160 million light years away, which is close. And they have the identical spectra. So now they now feel not only are they getting a bit of a new handle on the birth of galaxies, but we also have nearby examples to study that can give us greater detail as well. And this is an image now that's been formed both by Hubble and Webb. And it actually gives us the biggest time slice through history ever. It goes from around 10 billion to 13.5 billion light years. That's only 300 million years after the universe was formed. And then just released this week this is an image of a new solar system that's, what they say was 26 million years old. So there's 2 planets in it. The planets are formed, and this is actually the leftover material colliding and producing dust. So this is 5 astronomical units, 60 astronomical units. So that's from Jupiter to, well, a bit beyond Pluto, twice the distance of Pluto. So they were shocked at the resolution they got but twice the resolution. So now they can monitor over time how the dust planet is. So in other words, we're not watching planets form here. We're watching, remember we all heard that all the things bombarding to the moon and gave their asteroids, all these leftover debris. Well, here it actually is, and we're seeing it, which is quite extraordinary. And in fact, Webb just discovered its own first exoplanet this week as well. Now, before we finish, just to say that as incredible as all of this is, it's getting started. But the other side to remember is that it's in the context of a revolution that's going to go on in the next 5, 6, 7 years in astronomy you need to watch out for. Okay, European Southern Observatory are building the extremely large telescope, 40-meter wide mirror. They're literally building it right now. First light, 2027. We've got Gaia in orbit. It's still to release its best catalogs. I wish we could spend more time on this. Basically, let me just give you one example of what they're kind of saying they might be able to do with Gaia. they're going to monitor the real motion of 1.6 billion stars. They actually think from that census of star movement in the Milky Way, they'll be able to unwind the Milky Way through all of its revolutions in time. They think they might be even able to find out which other stars in the Milky Way were born with our sun. Just work it back. That's the kind of science we're able to do with what's called big data. You know, the scary AI, machine algorithms in there, looking for these patterns, right? The square kilometer array to be built in the 2030s, 5,000 radio telescopes with a combined area of it's about half a kilometer, even though they call it square kilometer array. But this is so powerful, it'll monitor 26 billion galaxies as buoys in the universe and literally map dark matter and dark energy. They say it could pick up a walkie-talkie 14 light years away. And then the LSST, this 6 meter stereo telescopes. Now, again, let me just put this in perspective this way. The best sky survey we have is called the Sloan Digital Sky Survey. It's a quarter of the Northern Hemisphere mapped by, I'm not sure how big the telescope is, probably about 3 or 4 meter telescope. And they release a new version of that catalogue of about 300 million stars every year or two. The LSST will map the entire hemisphere it's watching every 3 days down to magnitude 26 at the resolution of Hubble. So we'll get a new catalogue. They reckon it'll actually detect every near-Earth object down to 100 meters, every one. And it'll work with the square kilometer array to monitor. They're saying something like, I think, over 10 billion stars it'll monitor movement-wise, as well as 20-something billion galaxies. So it's not just Webb. There's 3, 4, and then the USA are building their 30-meter telescope on Mauna Kea, if they're allowed, because the people of Hawaii are not happy about it one bit. So, in summary, it's an amazing era in astronomy because it's kind of starting all over again. You know, it's like as if the European Southern Observatory and Hubble set the groundwork, lay the lay of the land, what questions to ask. And then these new telescopes are going to pick it up from there. And of course, they all have limits. You know, there's people not even born or in kindergarten right now who will be giving talks like this in 40 years' time with the next telescope. So it really is. I mean, I'll just say at my age, all my expectations when I was a kid have been met. You know, rovers on Mars, Hubble, they're all met. It is a truly golden era in astronomy. And to finish off, James Webb is really tackling 4 big questions: the first stars, the first galaxies, the census of exoplanets, and then really map our solar system material makeup in fine-grained detail.